All right, this tabular integration is for a specific kind of integration by parts. It only works in PE or PT situations, okay? It works in PE, polynomial, exponential. It'll work for that. And it'll work for PT, polynomial, trig. It doesn't work for ET. Okay? Any hunch why that might be? What type of property do exponentials and trigs have in terms of thinking about their derivatives?
They're like repeat, like they're cyclic.
Okay, they're cyclic, right? And so it would not work if both of them were cyclic, because if both of them are cyclic, you just end up in this never-ending cycle. So the only way to do the ET are where you do it twice, and then you move over one integral that matches the other as a common integral, like terms. That's the only way to tackle that. But if you find yourself with a PE situation, a polynomial with an exponential, so a polynomial has the property where it's going to descend in power. So its power is going to go from a 4 to a 3 to a 2 to a 1, and it's going to descend, paired with a cyclic. So if that's either a poly-exponential or a poly-trig, then tabular is a nice little quick shortcut that helps with that. Okay. All right, so you're going to start looking at the limit. U is going to be your polynomial for sure. The dv part will be your exponential or trig part. You'll run your polynomial down to 0. All right, so you're going to take that polynomial and take the first derivative, second derivative, third. You're just going to keep going, and eventually, ... you will get down to 0. Okay, that's true for every polynomial, where regardless of how high of a power, eventually you will get down to 0. On the cyclic side, you're going to run the antiderivatives over and over and over again an equal number of times. But it's just going to be a cycle. So that's not ever going to get to 0. It's just going to, if it's e to the x, it's just going to keep cycling through e to the x with the chain rule. If it's a trig, it's just going to keep cycling through sine to cosine to cosine to sine and back and forth. So you're going to run your antiderivatives. So the antiderivative, the antiderivative, whatever, just keep going all the way until you have an equal amount. Then you start pairing diagonally like you would in integration by parts. So the first pair, or you just ka-chunk, ka-chunk, ka-chunk. The first pair is just a positive pair. Okay, you're going to pair them with the plus. Then it would be minus, because that's how integration by parts works. And then it would be minus the next pair. And then the third one reverts to a plus again. But the only reason it reverts to a plus is because it's actually 2 minuses. It's a minus minus. What I want you to see here is that this is what's happening. You start with the UV combination. That's your first diagonal. Minus, and then you have your next, you have your u prime paired with your first antiderivative of v. And there's really a parentheses in front of that. And then you have another minus, and that will be your u double prime paired with the second antiderivative of v. So there's the first minus and the second minus. and there's actually a parenthesis in front of that. And then you'd have another minus, and you'd have a u triple prime paired with a triple integral of v, but there's a parenthesis in front of that. So that's why the sign keeps flipping, because this matches to that, but it also impacts that. But it also impacts that one, but so does this. Like, you just keep having, the signs keep changing because there's an even number of subtractions, and then an odd number of subtractions, and then an even, and then an odd, and then an even, and an odd. Eventually, you'll get down to the part where the last pair is going to be 0 paired with something, which is 0, and that you've reached the end of your possible pairings. So this is a shortcut to repeated integration by parts. So let's actually try this. So we identify x squared as being our polynomial, which means our dv is e to the x dx. All right, and we're going to take this through all the possible derivatives. So start with x squared, and then 2x, and then 2, and then 0. So take that all the way down. On the opposite side, we'll be doing e to the x dx, and its antiderivative is e to the x, and its antiderivative is e to the x, and its antiderivative is e to the x. So then we work combining the first derivative with the first antiderivative, the original function with the first antiderivative. So x squared is going to get paired with e to the x. And then we have a minus. And then 2x, which is the next one, will get paired with the next one, which is e to the x again. And then a plus. And then 2 will get paired with e to the x. And then a minus. And 0 would get paired with e to the x again, but 0 paired with anything is going to be 0. So that's not going to be a relevant part. And then we know we're done when we add the constant of integration. So we really don't need this part. That won't be part of your final answer. So the correct antiderivative of the original problem was x squared e to the x minus 2x e to the x plus 2 e to the x plus c. And you can always check your work by taking the derivative of each individual part, and it should clean up to be x squared e to the x. The thing that gets tricky here is if there's like chain rule you gotta watch out for, then it starts to, you just gotta keep it straight. If you have, oh, I got chain rule again, chain rule again. All right, so here's one with chain rule. All right, so we identify x cubed as being our polynomial. So we'll always start with x cubed, then 3x squared, then 6x, then 6, and then finally 0. On the other side, we've got sine 2x dx. So we start with that. That has to be the top thing in you're working through. And then you work through the antiderivative of that is negative half cos 2x. So remembering that the sign of an antiderivative is negative, and then the chain rule requires me to divide by 2. The antiderivative of that will be negative again, negative a quarter sine 2x. The antiderivative of that will be positive an eighth cos 2x, and then I need one more, so positive 16th sine 2x. All right, then we start matching things up. So the x cubed is going to match diagonally to the 1/2 x squared, and that's the negative 1/2. Now it's a positive combination, but since the other one is negative, the negative will trump over all, and so we'll have negative 3/2 negative 1/2 x cubed cos 2x. So our next combination would be the 3x combined down to the negative 1/4. And as I cross the negative in the middle, I also have the negative on the 1/4. So my overall answer is going to be plus. So that would be 3/4 x to the second sine 2x. And then let's see, we'll be able to see. Okay, sine combined diagonally down to 1/8 cos, and everything's positive in that situation, so that'll be a plus. 6 down to 8, so 3/4 x cos 2x. And then my last combination before I get to 0, that one combined down to here, but I need to remember that I'm crossing over a negative sign. So that'll be ultimately be a subtraction. 6 to 16, that'll be 3/8 sine 2x. And then the last combination would be a 0. So we just have to remember the constant of integration. Sometimes you'll see the answer in the back of the book written in grouped factored form. So they might group the cosine terms together and write it in group factored form, and then they would group the sines together and write that in grouped factored form. So that could be a possibility of how you see that. Does that make sense? Do you understand what I'm talking about? Okay. All right.